Yes, okay, we are now in record, and not much to see here. This is today's class. We're in the week of March 8th, and the Zoom materials for Friday, there are two items. First of all is this Word document, which it has a couple of the improper integrals we didn't finish this week. We're going to get to at least one of them today. I don't know if we'll have time to get to the second one. That page, it's called 03/21/2021 is this document right here. All right. Numbers 3 and 4, again, these are, we did 1 and 2 in class, and that'll be the first thing we take on today. And we're for sure going to do number 3. I don't know about number 4 because I have some other things I'd like to get done. Notably, this is what I would consider, these are the U substitution integrals that you guys wrote. Some of them can't be done. Some of them aren't U substitution. I think all in all, the ones that are U sub are pretty fair. And I would like to go over those as the second part of class. And then for the third part of class, I'm going to talk about something new, which, well, it's kind of new, kind of not. It's parametric equations. This is the lead topic of what you're going to be seeing. Let me think. Yeah, this is the My AP content, I believe. They're going to start with parametrics. I think this is their unit 10. And it's parametrics, vectors, and polar equations. And we're going to start with parametrics. We've done derivatives of parametrics already. This is going to be just applications of. So without further ado, I think we can, I'm recording. Okay, I think I'm good to go. So let's take a shot at number 1, or I guess it's number 3, this natural log here. These are the two I'd like to do, and again, I'm not sure I'm going to have time for it, are the ln of x over x squared, and the second one is 1 over x squared minus 1. Our first, and we can talk about both of them to start. Get my glasses on. What makes them improper integrals is the fact that we're going to infinity, and we're going to infinity. There is nothing in between the bounds, between the upper and lower bounds, that's causing a problem. What we're looking at is for the ln of x over x squared, we're talking about this area right here, which I hope you can appreciate has an infinite lateral dimension. Question is, does it have an infinite area or not? And for number 4, we're looking at, it looks like from 2 to infinity, so that would be about here. And we're looking at this area under the curve. And again, we've got infinite lateral dimension. Do we have infinite area? So before we do one of them, let's talk about both of them as far as the technique you would use for integrating. Neither one of these are U substitution. Hopefully you recognize that number 3 is going to be integration by parts. I'm seeing that logarithm, that ln of x, and that's just crying out for integration by parts. And for number 4, I think that's the easier of the two, is the partial fractions. Notice that the denominator factors to x plus 1 and x minus 1 as factors. It might be tempting to do a U sub on that, but if you try to do a U sub and you go with U equals x squared minus 1, you're going to get du dx is 2x, and this x right here is going to cause your world to hurt. So let's just, for now, let's just take the ln of x over x squared. If you guys on your own, would you please integrate that by parts? What I would suggest you do is, it is an improper integral. My advice for you is to just ignore the bounds. Let's just integrate it as if it were an indefinite integral, the ln of x over x squared. I shouldn't have to be talking now, so I'll let you guys get to it. Integration by parts begins by recognizing you got to fill the shelves. We've got a U and a du, and we've got a v and a dv. The entire integral, the integrand and the variable of integration have to be consumed, and they need to be occupying the u and the dv. We're going to use the ln of x as our u, and we're going to use 1 over x squared dx as our dv. Now you've got a tiny little derivative to take, and you've got a tiny little integration to do. Okay, there's where you should have landed if you did integration by parts correctly. Let's set this up so that we can attack this with our integration. Notice the negative signs cancel out, and to prepare this for integration, let's write this as x to the negative second dx. All right, there is our integral. All right, there are our antiderivative, I'm sorry. So let's, I'm going to erase the top. This is being recorded if you need to go over this again. So let me get rid of the top. Now we have to address the bounds. I want to talk to you guys about how we would properly write this. What we've got so far is, generally speaking, we've got the integral of the ln of x without bounds over x squared dx is equal to negative x over the ln of x minus 1 over x. Technically, it would be a plus c, but since we're going to apply bounds, we'll ignore the plus c. So that is the antiderivative of this. And now when we apply the bounds, we've got infinity that makes it an improper integral. So our rewrite of this is going to be as follows. Let's replace the infinity with a dummy variable. I like the way Karen Hires used b for the upper bound and a for the lower bound. So we're going to change that infinity into a b, and we're going to write it as follows. There you go. Now all that's left is to evaluate this. Plug in b into the antiderivative, plug in 1 into the antiderivative, and you are going to find that there's one indeterminate form that shows up, and we have to deal with evaluating that. I do have a typo in here, a rather significant typo. Let me bring Ruthie down a little bit. Let's take a look at this guy right here. I think when I wrote that, I should have written, I'm checking my answer key now. Apologies, guys. What we've got is, this is the ln of x times 1 over x. Okay, apologies. Now we have to evaluate this, plug in b for the x, and then plug in 1 for the x. The limit as b approaches infinity. As we evaluate this, what you're going to see is we've got negative infinity over infinity minus 1 over infinity minus, in this quantity, we've got negative 0 over 1 and then minus 1. And as we evaluate this, what we're going to have is we've got this negative infinity over infinity minus 1 over infinity plus 0 plus 1. This thing right here is going to 0. So the only issue we've got is with the term ln of b over b as b approaches infinity. Otherwise, this thing is either going to, wherever this limit goes is going to determine what that area under the curve was. If it goes to 0, which I think it will, then all we're going to be left with is just 1. So let's evaluate this guy right here. So let me scoots this stuff out of the way. What we need to sort of evaluate on the side is the limit as b approaches infinity, and it was negative ln of b over b, which again, it takes the form of infinity over infinity, which gives us a L'Hopital application. Which would be the limit b approaches infinity. Okay, the ln of, by the way, that negative sign, you don't have to worry about that because you could just as easily, it's technically infinity over infinity or 0 over 0. And this negative sign is a constant -1, which you could move out of the way. Just rewrite it as, let's say, negative the ln of b approaches infinity of the ln of b over b. And now after L'Hopital, we've got 1 over b over 1. And this evaluates to 0 over 1. And this term ended up being innocuous to just 0. And we do, in fact, end up the integral. And that's, let me clear out all of this. Our conclusion is that this integral, it converges. And we know that it converges to a value of 1. So that's the area under the curve. Okay. So anyway, that's an improper integral. I would suggest you do most of the heavy lifting, as in the integration part. Just treat it as an indefinite integral. Once you find the antiderivative, then go in and apply the limit notation so that you can write an improper integral as one that is kosher, so to speak. All right, let me see where we are on the clock here. Very good. Okay. Where I'd like to go to next is I'd like to go to our U substitution practice. All right. There you go. These are all the ones I'm going to show you guys. I'm going to avoid the awkwardness of calling on you guys and asking you to unmic and all that. So what I'm going to do is I'm going to zoom in on the whole set, and we're going to go through all 18 of them. I'm going to set the, I timed this before we started, and I think it takes me about 10 seconds to do each one. So I'm going to give you guys 10 seconds to hopefully do these in your head. That's the goal. These are the kind of integrals that you are seeing the MyAP instructors doing it. They're basically saying just apply a constant, and they are integrating these in their head. I think 10 seconds is a workable amount of time, and as I'm recording this, you could just be writing these down, and I'm not sure where you're going with this. I hope your goal isn't to just memorize all of the integrals and the antiderivatives on every single card. That's not really the best strategy. Would we agree? So let me zoom in, and it's possible I make a mistake. Call me out when I see you guys in class next week. I'll probably call myself out when I rewatch this video for editing. But wow, is that big enough? All right, so there we go. I'm going to set, that's too big. That's fine. Okay, I'm going to set my phone to stopwatch. I'm going to give myself 10 seconds to set this thing. Okay, that's 10 seconds. Now what I'm looking for in this is I see this as 17x squared minus 394. Eric, is that you? To the fourth over 4 plus c. Okay. Yeah, that's it. All right, let's go to the next one. If you, by the way, if you're not sure, you can do these on your own time with USub paper and pencil. Okay, 10 seconds, go. All right, that's 10 seconds. The integral of this is the negative ln of the cosine of x. Right? I will give a little bit of prompting to this. This is the sine over the cosine. Recognize that the derivative of the cosine resides right there. We're going to be using a natural log rule. And in order to do that, our U substitution is the technique we've got to use. And notice that the derivative of the cosine is within the integral, except we are in need of one thing. We need a -1. So I put a -1 there, and we end up with negative ln of the cosine of x plus c. All right, number next. 10 seconds, go. Okay, first of all, don't forget the dx when you write your integrals. This is 1/3 quantity 3x minus 1 to the third over 3 plus c. 10 seconds, go. Okay, this one is 6/5, -6/5 cosine of 5x plus c. If I got one wrong and you guys would like, I'd appreciate it if you tell me. I'm pretty sure these are good. We'll be doing these in class as well. If again, I encourage you guys to be working along with me. This is not a U substitution. This would not be a question. By the way, the integral of the sine is the negative cosine. So the integral of the negative sine would be the positive cosine. So, okay. All right, what about this guy? 10 seconds, go. I was watching the stopwatch and then I peeked and I looked and I don't think this is a U sub candidate. No, this is not a U sub candidate. That one is. I think this is at the deep end of the pool as far as difficulty levels. Give it a shot. I'll tell you what, I'm not even going to put this one on the clock. I think this needs a little bit of paper and pencil help. Does it? Okay, recognize that we've got, we're going to be using a power rule. The argument of this is the ln of x, and the derivative of the ln of x is 1 over x, which is sitting right there. Yeah, this is, never mind. I think this might have been a do it in your head question. Give it a shot. All right, there's time. This is the quantity ln of x to the third over 3 plus c. Let's go to the next one. Oops. Again, we're being a little bit sloppy with our dx here. Don't forget you should have your variable of integration. 10 seconds, give it a shot, go. Your antiderivative of this is the sine, the quantity of the sine of x squared over 2 plus c. Okay, 10 seconds here, go. We need a 3 in order to make this thing go. We're going to use an exponential what we're integrating is what's actually coming out, or the byproduct directly out of the antiderivative is going to be that e to the x to the third. We need a 3x squared to make it happen, and we don't have the 3. So the antiderivative is going to be e to the 3x squared, or e to the 3x to the third, that quantity over 3 plus c. Again, if you'd like to confirm this paper and pencil on your own, do a u substitution with u equals x to the third. Well, that's a good one. Good, solid, simple. This is textbook. Do it in your head, u substitution. 10 seconds, go. The derivative of that 6x is 6, so we need a 6. We're going to balance it with a 1/6. So our antiderivative is going to be 1/6 times the quantity 6x to the 8th over 8 plus c. Okay, 10 seconds, go. We're doing a trig rule. I see the argument of that trig function is 4x squared, and we need an 8x, and it's sitting right there in the integrand. So we don't have to u sub anything in. We just know that coming out of this, we should have the cosine of 4x, the cosine of the quantity 4x squared plus c. And we got one more. Did we do this one already? Did I copy this twice? Oh, this is a variation of the first one we did. 10 seconds, go. You got your answer? Okay, notice we're doing a power rule, something to the third. So we're going to use power rule of integration. In order to make this happen, we need the derivative of the argument, which is the derivative of 17x plus 394. So we need a 17. So we're going to balance this out by integrating, and our antiderivative is going to be 1 over 17 times the quantity 17x plus 394 to the 4th over 4 plus c. I don't know, is this working for you guys? I feel like I am doing a solo act here, which is kind of awkward. It's a lot more fun when we're doing this in class. Okay, I got one more column. Let's just finish this up. I'll try to be quicker. I got to say though, when you write an a integral, where's that dx? Come on, let's go. Tighten that up, guys. We're doing a power rule. The argument of that something to the squared is 4x plus 2. We need a 4. Therefore, our antiderivative is going to be 1/4 times the quantity 4x plus 2 to the third over 3 plus c. 10 seconds, go. Okay, we're doing a trig rule. I see that we're doing the cosine, whose antiderivative is the sine. We need the derivative of the argument, the 3x. We need that 3 in the integrand, so we'll put that in and pay for it with a 1/3. Our antiderivative is going to be 1/3 the sine of 3x plus c. I'm kind of nervous how many mistakes I've made when I go back and edit this. 10 seconds, go. All right, we're using the power rule. Something to the 5th. That something, that 3x plus 2, its derivative is 3, so we need the 3 somehow in the integrand. So we'll put the 3 in, we'll balance it by multiplying by 1/3. So our antiderivative is going to be 1/3. Quantity, 3x plus 2 to the 6th over 6 plus c. Ooh, this is a good one. All right, 10 seconds, go. It's time. Okay, what we're looking to apply is a natural log rule of the x to the third plus 3x. Now the argument of that logarithm of what we're using to do the natural log rule is 3x squared plus 3. And notice in the numerator we got x squared plus 1. If we multiply by 3, we've got 3x squared plus 3. So that what your u substitution, if you were to do this with paper and pencil, would be u equals x to the third plus 3x. Okay, if you're doing this in your head, then you're multiplying by a 3 that's going into the numerator. So we get 3x squared plus 3. You've got to pay for it with a 1/3. So our antiderivative is going to be 1/3 natural log of the quantity x to the third plus 3x plus c. Jordan, is that yours? You seem to write these devilish ones. Okay, 10 seconds, go. This has got some challenge to it. What you want to recognize is our antiderivative rule is going to be the power rule. We've got something to the 1/2 power. Now that something is 16 minus x squared. We need the derivative of that to be in the integral. So the derivative of 16 minus x squared is negative 2x. I see we've got a 4x sitting there. So let's factor out a 2. Let's factor in a negative 1. So I'm reading this as negative 2 times the quantity 16 minus x squared to the 3/2 over 3/2 plus c. Thanks, Jordan. All right, I believe this is the last one, and I'm going to do a little writing on here. First of all, guys, dx. When you write an antiderivative, you need the variable of integration. And if you can integrate this one analytically, you will probably get a full ride to MIT or some other prestigious school of mathematics, because this one has never been solved. We can do this in a variety of, we can approximate it, and we can, eventually we're going to be able to do a power series approximation of this. But as it stands, e to the x squared cannot be integrated. Now, what we can do is we can modify this. I can rig the game so that you can integrate it. If I were to, instead of writing this as the integral of e to the x squared, I had written it as the integral of e to the x squared times 2x dx. And notice your u substitution for this. U would be x squared. Your du dx equals 2x. Solving for dx. Look at this. What am I doing? I just like we're doing integrals. Du over 2x. And look what happens when we do our u sub. We've got the integral of e to the u times 2x times du over 2x. These things cancel out, and we're left with e to the u plus c. So if this 2x had been included in this original integral, then our result would be e to the x squared plus c. Okay, and that lightning round of 18 will be, there's other questions. I'll probably ask for some more cards from you guys, but there we go. Hopefully you're comfortable with those. I will listen to myself as I edit this tape. If I catch myself making a mistake, I'll try to highlight that. Otherwise, I stand by the answers. If you guys caught me with a mistake, let me know. If you're not sure how to do these, then it is on you to confirm in writing with the u substitution what my antiderivative was. Don't take my word for it. Don't trust anybody over 30. That's what they used to say back in the 60s. So there you go. Let's see where we are now. We've got about 25 minutes till the end of class. I want to go over parametrics real quick. We probably won't get to this fourth one here. This is the 1 over x squared minus 1 is integration by parts. And this does converge, and it converges to a value of negative 1/2 times the ln of 1/3. You might be saying, wait a second, that is an area above the x-axis. Why is it negative? Well, the negative 1/2, let me write this out. I'm getting distracted here. The area ends up being negative 1/2 times the ln of 1/3. Negative 1/2 is a negative number. The ln of 1/3 is also a negative number. So it is going to come out to a positive, albeit messy, positive number. So if there's, again, the answer ends up being -1/2 ln of 1/3. All right. Let's get to the parametrics. A parametric equation is kind of, the analogy I used was an Etch-a-Sketch. It's it's like you got the dials of an Etch-a-Sketch, and the X parameter, as you twist that dial, the little marker that makes the line on your Etch-a-Sketch screen goes horizontally left and right. And then the Y parameter is the little dial that makes the device go up and down. And they both move as a function of time. If you've seen people that, or if you have played around with the Etch-a-Sketch, you can make some pretty good curves if you can coordinate the spinning of the both dials together. That's the nature of what's going on with the parametric equation. The first 5 are just to turn this parametric equation into an equation in terms of X and Y. Your strategy for the first 2 is just going to be to use substitution. Okay. What you do is you find whichever one of these is easier to solve for t. In this case, I think that x equals t plus 1 becomes t equals x minus 1. And then there's the y parameter is defined in terms of t, so just take that t out, replace it with x minus 1. I think it becomes y equals 2x plus 1. This, on the free response, that would be fine. I doubt if it were a multiple choice question, it would show up like that. All right, let's take a shot at number 2, please. What I've written, 54 times the quantity x over 3 to the third minus 3 is correct. I would think you'd probably want to write it as 2x to the third minus 3. If you were, especially if you were planning to use that equation later for further analysis of something, or if you were just looking for an answer to a multiple choice question, I don't think you'd see it written like this. I think it's going to show up like that. All right. Now let's go to the trig ones. There's a little bit of trickery afoot as you have to work through these. Mostly you want to use variations of the Pythagorean identity for these. Let's square everything. Ultimately, what we're working for is if we can get a sine squared plus cosine squared, and if we can manipulate these two equations into that format, we can take the sine squared of t plus the cosine squared of t and end up with a 1, and abracadabra, there's no t. So if we square both sides of the first equation, we have x squared equals the sine squared of t. And if we do the same thing to the second equation, y squared equals cosine squared of t. And then what we'll do is we'll just add them together. And we've got, back to red, x squared plus y squared equals sine squared plus cosine squared, which is 1. And this actually is the equation for a circle. It's at the center, it's at the origin with a radius of 1. So that's what's written in parametric form is the parametric form of the circle, right? Let's take a shot at the one to the right. It's going to require a variation of the Pythagorean identity. I don't have it memorized myself. I know that the sine squared plus cosine squared equals 1. So to get tangents and secants involved, I'm going to divide everything by the cosine squared, cosine squared, cosine squared. And what that leaves me with is tangent squared plus 1 equals secant squared. All right, so to get rid of that tangent t and secant of t, we got to manipulate our equation by squaring, and then we're probably going to want to set it up so we can find tangent squared minus secant squared equals -1. Well, that should be. Or I'm looking at my answer key and I wrote it this way. I wrote secant squared. This might be how Alioth taught you guys. Secant squared minus tangent squared equals +1. So let's try to manipulate towards this format. So I'm going to start off by squaring the y side. So we've got y squared equals the secant of t squared. And then I'll square the x parameter. So we have x squared equals the tangent of t. Did I say t before or x? Tangent of t squared. And what we need to do is we're going to take the one equation and we'll subtract it from the other equation. And we're going to have y squared minus x squared is equal to the secant squared minus the tangent squared, which is simply 1. Okay, this is a finished form. I guess we could write it as y squared equals x squared plus 1, or y equals plus or minus the square root of x squared plus 1. All right. And the last one, let's see. This one is going to require a little bit of trig identities. I have a hard time believing that this is something that you would see on the AP test, because in order to see this on the AP test, you would you have to be brushed up on your trig identities. I'm just going to give you how to get to there. The identity you want to search for is the cosine, the cosine of 2 theta is equal to cosine squared minus sine squared. Okay, so what we're going to do is we're not going to do anything to the y equation. We're just going to leave it intact. We're not going to leave it intact. We're going to rewrite the cosine of 2t. Let's start off by squaring the x parameter. So we've got x squared equals the sine of t squared. And then let's take the y equals, and let's just use the identity cosine squared t minus the sine squared of t. And what we'll do is we'll add these two equations together. And what we end up with is the x squared plus y is equal to the cosine squared of theta. And then to get out of there, you've got to use another trig identity. Oh my gosh, trig identity is that the cosine squared. I'm so down a rabbit hole, I'm sorry. And this should be t, by the way. The other identity you would need is that the, let me push the identity up here in the corner. You know what, I'm sorely wasting time here. Apologies. The identity you're going to want to use is cosine squared of theta is equal to 1 plus the cosine of 2 theta over 2. So this ends up, notice that the cosine of 2 theta is equal to y. So this ends up being 1 plus y over 2. Yeah, we end up with y. Here's my answer to this. I'm down a rabbit hole. Y equals 1 minus 2x squared. I'll double check that when I rewatch. That one was painful. The main reason was just because it's a trig identity. This is more of a pre-calc question than it is a calculus question, and I would bet one of Schaefer's dad's pecan pies that would never appear on an AP test. So where I want to go to is the good stuff here. Derivatives of these guys. Do you remember the derivatives? Yeah, let me get some room. And let's just do, I'm going to look at the clock here. 57, I've got 7 minutes. This should not take too long. What you want for the derivative is what we're looking for is we want dy dx. And where we're going to get that from is if we have dy dt over dx dt. The dt's in essence cancel out. See that? And that's how we end up with dy dx. So let's get those derivatives each. The dy dt, that's this one here, is going to be -2 sine of t. The dx dt is 4 cosine of t. And that is the derivative. Let's real quick, let's do the first derivative of the second question. Dy dt equals, I'm sorry, dy dx equals dy dt over dx dt. Right, the dy dt, that's the derivative of this thing, is going to be 1 over t. And this 1 over t, x is equal to t to the negative first. So this would be -1 t to the negative second, which, oh my word, does that simplify? I have this written. I'm just going to wing it. Let's see. This is 1 over t over -1 over t squared. It looks like this just ends up being -t is our dy dx. All right, let me confirm that. Yeah. Okay, so now what's the second derivative? Okay, this might be the first truly new thing, so let me make sure I get that in before we're done. What you do to get the second derivative is you've got to take the derivative of however you simplified the first derivative. So like if we ended up with this, you'd have to use the quotient rule. If you simplified and went to here, you just got the power rule. But the second derivative is going to be the derivative, is going to be the derivative of the first derivative, but then you've got to put it over dx dt. So don't lose the fact of what dx dt is. Dx dt is right there, and dx dt is right there, or if you prefer, right there. Okay, so the second derivative, let me do what I think is the easier one. Let's take a look at the one with the cosines and the sines. It's probably easiest if you rewrite this thing as -1/2 the tangent of t. Now the second derivative of this, d2y dx2, is going to be this derivative right here. You can do the quotient rule if you want. I think it's much easier to just take the derivative of this, which would be -1/2 secant squared of t over, just rewrite this, 4 cosine of t. All right, so let me just double check everything's working here for me. Yeah, I think when I actually simplified this as -1/8 secant to the third of t. Those are equivalent. This would probably be your multiple choice answer. This one is correct though. And last one is, let's take the second derivative of the blue equation. I'm so out of time, I just got to call it the blue equation. So there is some benefit to simplifying, because if you don't simplify this thing, you got to take that quotient rule of 1 over t over -1 t to the negative second, or you could just take the derivative of this. So the second derivative, d2y over dx squared, is, well, the derivative of the first derivative is going to be -1, and put that over probably this, -1 over t squared, which that thing is going to simplify. Isn't that simplify just to t squared? Let me just double check here. Yeah, there it is. This is t squared. Okay, and we are in the preview phase of the day here. I'm just trying to show you guys what's coming when we get into parametrics. You're going to find that vectors are similar, and I am at time. I'm going to make a recording of this, so if you are so inclined to review it, or if for some reason you glitched out and you missed it, it'll be available to you. Otherwise, I am out of screen mode, and have yourselves a great day. All right, be well.